Hey, hi everyone, I'm Juan Lini Domingo, and this video will be a general introduction about using time-resolved classifiers in EEG. So we will talk about what is a classifier, some general differences between linear and nonlinear classifiers, and about some points regarding using linear classifiers in EEG. So in cognitive neuroscience, several questions that we have are related to compare or contrast the neural states that are associated to two or more conditions. For instance, let's imagine that today our question of interest is to understand how the brain can discriminate between different types of visual inputs, like animals and objects. So we can present picture of animals and picture of objects. I will use this example based on animacy for two main reasons. The first one is because it's something that you're going to find in the literature easily. And the other one is because the practice that we are going to run later or we are going to do is going to be based on this kind of data. So neural imaging techniques like EEG or MEG are highly dimensional. This can make more complicated to find differences when the experimental condition, in this case animacy, are represented as complex patterns in a high-dimensional space. So we can imagine that the neural pattern associated to animacy, or animal versus object, not only differs in one electrode, but in several electrodes and showing a complex pattern that a priori we don't know. In this kind of scenarios, we can think of applying MBP approaches and machine learning or RSA. So just to give you an idea of what we are going to see in a second, a classifier is going to be a function that after being trained with a lot of observation is going to help us to find a rule to categorize a new observation. Let's take a look. First, let's think about a low-dimensional scenario. So imagine that due to a very low budget, for instance, you can only afford an EEG system with two electrodes. Although you only have two electrodes, that they are here represented in the x-axis and in the y-axis, and we can see the voltage of each, you are still really interested in studying how the brain processes animacy. So in your experiment, you can display on the screen several pictures of animal and object and register the voltage associated to each image in these different channels. So you can show one animal, could be something like that, and one object. Then at the end of the experiment, you will have a lot of trials. We can call this dataset our training dataset. A classifier will do something very simple with this dataset. It will try to find a rule to classify the data based on the feature we are using, in this case, the voltage in two different channels. What a linear classifier will do, it will be trying to find a line, or the best line, that distinguishes between classes. So now in the upper part, we have animals, and below objects. But how good is this classifier? To know this, we will use a different dataset, and we will test the accuracy of the classifier in this new trial. We will take a look what is to the real class of this trial and see how many times the classifier worked well. In this example, the classifier worked well in 70% of the cases. That is not bad at all, given that the chance level of classifying a trial currently here is 50%, since we have two categories. But we will talk about estimating the performance of a classifier in a different video. Keep in mind that in a more realistic scenario, we are not going to be working with two features or two channels. We can work in EEG with hundreds of electrodes. So visualizing this figure will become a little bit more complicated. So keep in mind that in that case, this line will be an hyperplane, trying to separate different classes based on a lot of dimensions. So far here, you saw two or three important steps of a classifier: training and testing. And we will talk about cross-validation in a different video. So in our previous example, we saw how linear classifiers can divide both classes using a linear model. However, we can imagine a different way to divide both categories, so fitting much better our testing dataset. For instance, we can go beyond linear classifiers and imagine a more complex non-linear model, something like that. By the way, to simplify, we are talking all time here about binary classification, but linear and non-linear classifiers also work with more than two categories. We can find several types of nonlinear classifier, like kernel support vector machines or k-nearest neighbors. Nonlinear classifiers are a really good tool or good option to find a more complex structure in the data. For example, in this case, a linear classifier will have problems to divide the data using a line here, right? However, a nonlinear classifier will be able to create an accurate model. So some nonlinear classifier has been classically used in fMRI studies, and the main reason for that is that these functions can do a better job when we have a high number of dimensions, like thousands of voxels, but only few trial or exemplar in our per category. In general, keep in mind these three main features of nonlinear classifier compared to linear classifiers. So first, they will allow you to find more complex model in your data. Second, they will have a lower empirical risk. That means that they can create a better model for your data. For instance, if you take a look to this figure, you can expect a nonlinear classifier will fit your data much better. And third, they will have a higher expected risk, meaning that they will probably generalize worse to other datasets, probably because they are overfitting your data. Let's take a look to some scenarios to see how linear and nonlinear classifier can have problems to generalize their model. So imagine that after training your classifier with very limited number of samples, you continue collecting data and getting closer to the real distribution. So that will allow you to see whether your classifier was under or overfitting your data. For instance, in this case, is that the non-classifier model is correct, the alternative model will be underfitting. However, if the linear model is more accurate, the nonlinear model will overfit. Okay? But the question is, which model should we use? In general, as you can see in this figure, the higher the complexity of a model, the lower the empirical risk, but make a lot of sense. But unfortunately, it will generalize worse. And as a general norm, we should always pick the model with the smallest generalization error. So we should choose carefully. Let's take a look now to the linear classifiers. There are different kinds of linear classifiers, but during the course, we will mainly use linear discriminant analysis, LDA, which has been traditionally used in EEG and MEG studies. One of the main reasons is that EEG generally fit its main assumption. So the first assumption is that the feature of each class must be normally distributed. The second one is that the Gaussian distribution of all classes have the same covariant matrix. This is not always the case, but it seems that LDA is still quite robust when this assumption is not achieved. And third, suppose that we know the true class distribution, and of course this is a theoretical assumption that we cannot achieve in the lab. In general, with EEG, the ratio between the number of features and exemplar per classes are more balanced than in fMRI studies. However, when we have a lot of features, like a lot of channels to train and test our classifier, but not a lot of trial, it is very recommended to use LDA with a modified covariant matrix. This is also known as a regularized LDA, and we will use it during the course. But if you want to have a better understanding about this, I really recommend you to take a look to this paper. In general, remember that LDA is less likely to overfit, but also require this careful regularization. Now that we have a general overview of linear classifier, let's move back again regarding how this tool can be applied in EEG and MEG dataset. where the high time resolution is one of the main features of these techniques. So in the last year, we saw in several studies how classifier can be applied in a time-resolved manner in EEG and ABG. That is, we can run the classifier independently per data point and normally per participant. So we will train and test the classifier in a given time using information from only that specific time point. Then we will move to the next data point and so on. This way we can see how the accuracy of our classifier evolves over time. So here we see real data of one participant where I try to decode item animacy using the raw EEG signal. You can see the accuracy of the classifier seems to become higher than chance. Chance is around, it's supposed to be 50%. So we have two categories, animal or object. So after the first 100 milliseconds, it seems to have we have better accuracy, and we have a decodability peak around 150 milliseconds or less. However, as you know, EEG signal is extremely rich, and probably you're wondering which kind of information we want to use to feed and test a classifier. We can use just raw EEG signal from all channels, but also we can use information extracted from time frequency analysis. For example, you can use as feature for the classifier the power in a given frequency band. This kind of selection will depend on your research question. If you want to test how theta power is carrying information related to animacy, you can use theta power from all your channels. What you should always keep in mind is the assumption of the classifier and the nature of the feature that you will use. For instance, if you are using or you are interested in using the phase in a given frequency band, keep in mind the circular nature of this signal. Probably it makes more sense to use an RSA approach with a circular statistic package or something like that. So really depends on you and what are your questions. Saying that, let's continue imagining that we will use raw EEG, but it's the more general practice and something that we are going to do also in some of our practice sessions. As you know, in a typical EEG experiment, we can end up with a huge matrix of data. So 24 participants, 800 trial, 120 channel, and 1,000 of data points. And something that we will probably do is to apply some dimensionality reduction for a lot of reasons. One reason to do that is to avoid having more features to train and test the classifier than data points. Imagine that you are using the voltage in 128 channel as features, but you only have 80 trials, like 40 trials per category. That's something that we should avoid since it might overfit noise in the data. Other reason to reduce the number of features in EEG is that channels are not independent and there is redundant information. Some neighbor channels normally carry similar information. And finally, something very practical about dimensionality reduction is that we want to reduce the amount of time that our analysis will take. And yes, this will have a clear impact on that. Regarding dimensionality reduction, there are some general practices, and here we are going to see some of them, but just few examples. The first one is to use principal component analysis to extract the main component of your data. Then, instead of using all your channel, just use for your classifier those components that explain a significant amount of variance in the signal, like let's say 95% of the variance, something like that. This can make a huge difference moving, for example, of having 128 electrodes to 40 or 60 components to fit your classifier. Other common sense practice, of course, is to reduce the time resolution of the signal. For instance, you can downsampling your data. It will reduce dramatically how long the analysis will take, and in general, will not affect significantly your results, so no problem. Apart from dimensionality reduction, there are other general practices that you can see regarding how to treat the classifier inputs. For instance, try to increase the signal-to-noise ratio. One way to achieve that is to average trials that belong to the same category. So imagine that you have 1,000 trials in each category. So instead of using all trials, you can randomly take 3 trials and average them, resulting in 1/3 of the exemplar per category, but here some of the noise should be reduced. Then you can repeat this approach several times, taking different random or pseudo-random groups of trials to produce a better estimate of the classifier output. Another common practice that you can find is using a sliding window approach, that it will work as a kind of a low-pass filter in your signal. But in general, of course, there is no better practice than having a good paradigm and, of course, collecting a huge amount of trial per category. Anyway, if you want to read more about this topic, I strongly recommend you to take a look to this tutorial where the author nicely shows how classifier performance can change depending on how you are treating the feature that you will use for your classifier. So before having our first contact in a practice session with a linear classifier, I wanted to briefly mention one LD output that we are going to use during the practice. This output is going to help us to calculate the performance of the classifier even in a trial level. So this is just, this output is the distance to the hyperplane. So when a new trial is tested in a model like this one, we will obtain a value that is telling us how far is this point or this trial to the hyperplane. In a binary classification, the sign of this d value will tell us to which category the trial has been assigned. That is totally up to us. We can say that positive values are associated to one category, like animals, and negative to the other category, like objects. Also, apart from the sign, we can also check how far is this data point to the hyperplane, giving us a parametric measure that we can use on a kind of index about how confident is the classifier assigning this trial to one category. So the bigger the distance to the hyperplane, the more confident. Okay, so here I just wanted to let you some useful reading and one excellent MBPA toolbox for MATLAB that I strongly recommend you to use is this one, the MBPA Lite. We are going to use some function from this toolbox. That's it for now. So see you later in the practice session.